In this webcast, we're going to perform a stereochemical analysis on the configuration of fructose bisphosphate that's shown here. This configuration was derived from glyceraldehyde 3-phosphate, and we want to understand which of the two different faces of that carbonyl must have been attacked by the enolate in orange in order to achieve the configuration here. So our goal is to look at addition to both sides of the two different aldehyde faces in glyceraldehyde 3-phosphate and match, that's the key word, match the stereochemistry that we see in the product fructose bisphosphate. It may be helpful if you would go ahead and construct a model of the glyceraldehyde 3-phosphate like I have drawn for you here. Here's the aldehyde portion, and basically what we're going to do is look at attack from the top face and the bottom face. Now, what kind of faces does glyceraldehyde 3-phosphate have? Well, the faces are diastereotopic. You can convince yourself by doing the Q-test or simply adding a nucleophile to one face and then the other. Since there's already a stereocenter in the molecule, you can see 4 different substituents on the alpha position. Since there is already a stereocenter in the molecule, it should be clear that we'll obtain diastereomers when we attack the two different faces of that carbonyl. In the top diagram, what I have drawn for you is the 4 atoms that make up the plane of that carbonyl carbon, the hydrogen, the carbonyl carbon, the oxygen, and the alpha carbon. Those atoms are all in the plane, and we want to know which face we're looking at. So you can see we're looking at the ray face. How do we know that? Just as a reminder, if I go through and prioritize the substituents, oxygen is 1, that carbon that's alpha is 2, this hydrogen is 3. So as I'm looking above, which is the direction that this enolate is attacking from, you can see that from looking from above, the priority is 1, 2, 3 in a clockwise direction. That would represent the ray face. So at the top, we're looking at ray face attack, and basically that's what we want to know. Which face does the enolate attack? Is it the ray face or the psi face that leads to the configuration that's shown down here? Well, we're not going to worry about the details of the enolate. We're just going to call that orange portion, everything that's over to the left-hand side of this molecule, the enolate, and what we're really focused on is how to generate that stereocenter there. And what we need to do, and this is where your model will come in play, is to imagine as the nucleophile attacks this carbonyl carbon, say from the ray face, how does that rehybridize from an sp2 trigonal planar geometry into a tetrahedral geometry, and what's the stereochemistry that results? So let's just go through that process, and I'm going to try to do that, illustrating each position on the right-hand side. So first, this is the alpha position, and it already has a stereocenter. And so if we just align this with the 3 atoms that are highlighted here, starting with the carbonyl carbon centered on the alpha position and to the right the CH2, if we put that with that V pointing downward, you can see that as we have that in the plane, so that's going to be positioning just like that, and I see, to me, the hydroxyl group coming straight out at me. That's where I know that that position has to be. That's kind of like my point of reference. So the hydroxyl group will be coming out, and now with the enolate attacking from the front, the hydrogen atom positioned in the plane. So now in this next V, hydrogen, carbonyl carbon, alpha carbon, and those 3 atoms right there, then the enolate will be coming out in the front right there. The enolate should be in the front, and the O- will be in the back. Now my goal is to match the same exact orientation that's drawn down here, where I have in the plane the 3 atoms, the enolate carbon, that is going to be the nucleophilic carbon, what was the carbonyl carbon, and that needs to be pointing upward to this 3 carbon atom V, and then the right-hand side, on the right-hand side is this already defined stereocenter. Notice that I have this hydrogen atom here instead of the enolate alpha carbon, or the enolate nucleophilic carbon, and so I need to move the enolate into the position where hydrogen is. And so I can do that if I had my model, or I can do that mentally in my mind, and what I really am doing is rotating about this carbon-carbon bond. So when I do that, the enolate occupies the position where the hydrogen is, and as the hydrogen moves into the position where the oxygen moves where the enolate was. And so all three groups are going to permute or interchange with one another, leading to the structure that's shown here. The hydroxyl group in that position doesn't change, but notice that the oxygen configuration, which once protonated will become the alcohol, does not match the configuration here. We can guess that Ray phase isn't the right attack, probably psi phase is. Let's go through that process and make sure that that outcome is correct. So you can prioritize in the same way. Convince yourself that now we're looking at the psi phase. Oxygen is number 1, carbon is number 2, this hydrogen is number 3. Again, I've basically taken that carbonyl group and was oriented like this. In the top diagram, we were attacking the Ray phase. We're flipping this around 180 degrees, and now we're attacking the psi phase. And so that's exactly what I have with priorities like that. The direction of rotation, as my eye sees it, is in the counterclockwise direction. That's the psi phase attack. So here we're going to end up with the hydroxyl group now pointing, because of the reorientation, flipping this molecule 180 degrees, that hydroxyl group is pointing in the back. That's the position that is represented for you in the fructose bisphosphate here. And so you can see that our reference point, notice the V is pointing down here and the V is pointing up, so we're going to have to flip that molecule over in just a moment. But before we do that, let's go ahead and do the enolate addition. When the enolate comes in from the front side or top side, we're going to leave that hydrogen position, but the oxygen will end up going to the back. Think about the attack and rehybridization that takes place from a trigonal planar to this tetrahedral carbon atom. So oxygen is going to go into the back, and enolate will come out into the front. Now, we need to get this position exactly the same as this position, and so we need to take that product and flip it over 180 degrees. That's what is going on here. We're just physically taking that product molecule and flipping it around 180 degrees. So zigzags that were pointing up like this now begin to point down and in the right orientation. So in particular, we've got that structure pointing down, and the configuration at this position has swapped the enolate and oxygen atom when that rotated 180 degrees as well. We have this hydrogen in the wrong position, and so we need to do that bond rotation again, and what we're going to end up doing is positioning the enolate in the plane. We need that enolate nucleophilic carbon in the plane, and so we're going to rotate in the direction that the arrow shows, like that. The enolate will come to where the hydrogen will come where the oxygen is, and the oxygen will go to where the enolate is. And so when we're all done, we end up with a configuration that's like that, and it matches the product, that fructose bisphosphate. So now we can conclude the key finding that the enzyme, in order to achieve the stereochemical outcome that you see, has to have the nucleophile attack only one phase, only the psi phase. Somehow the Ray phase has to be positioned, so here's the substrate, here's the enzyme. Somehow the enzyme is able to block the psi phase from attack so that it blocks the Ray phase from attack so that only the psi phase is able to undergo reaction.